She's visiting us for the rest of the week, so that will be kind of introduction to what she's doing, and everybody's welcome to chat with her while she's here.
Okay, thank you very much, and thank you for the invitation. I was pleasantly surprised that there are some familiar faces around, well, not here in the audience, but yes. Good, so this is work that I did in collaboration with Arcaded Cycling at Imperial College London, and it's about the scattering on effective strings and also membranes. So let's start with a motivation of why we started this work. And the motivation comes from the big success of the last 10 to 15 years to try to understand the worldsheet theory of confining strings. So there have been a lot of developments, and in particular for the simplified question of considering an infinitely long string in the large n limit of Curie-Mills theory. So you can think of it as we were seeing this morning in the talk by Gabriele, having a quark and an antiquark pair and a very long string stretching between the two. And because of this large n limit, the self-interaction of the string is suppressed, so you don't have these glue balls that Gabriele was mentioning this morning. So on the two-dimensional worldsheet of the string, you then have a unitary field theory, and the question is, what is the action that describes this long string? So let me just briefly summarize these advances that have been made in the last 10 to 15 years, because this will be relevant for the rest of the talk. And also, there will be some terms that will appear, and I will explain them in more detail afterwards during the talk, so it should be fine. So in the low energy limit, the action is very well described by just a Nambu-Goto action in static gauge. And in the S matrix on the worldsheet of this action is proportional to the identity in critical dimension d equal to 26. And this is a very nice observation. In fact, this comes from the fact that in d equal to 26, the Nambu-Goto action in static gauge is an integrable TTbar deformation of a free theory of just a collection of free bosons. And the TTbar deformation can be constructed for arbitrary dimension d, also not necessarily in the critical dimension, but also in other dimensions, in particular d equal to 3 or d equal to 4, which makes it particularly interesting to apply to QCD. And using this description as a TTbar deformation, one can obtain the spectrum, so one can compute physical observables using integrability techniques, in particular the thermodynamic Bethe-Ansatz. And in this talk, I would like to understand what happens for the membrane. So when you take a higher dimensional object, which has a world volume, so d is equal to 3, instead of the string where there is a two-dimensional worldsheet. So the plan of the talk is the following. First, I will give some generalities about S matrices for two-dimensional integrable theories, just to tell you what I mean when I say the theory is integrable. Then I will review the story about the S matrix for the Nambu-Goto string and describe the integrability that we have there. And then in a third part, I will come to the work that we actually did, which is the S matrix on the three-dimensional membrane. And then I will compactify this membrane so that I have an effective two-dimensional description and look at the integrability of this two-dimensional quantum field theory. And then I will end with some conclusions and an outlook. So this is supposed to be an informal talk, so if you have questions, interrupt at any point. So let's start with some generalities about S matrices in two-dimensional integrable field theories. So integrable theories, they have a lot of conserved charges, and this constrains the dynamics very much. In particular, it will constrain the scattering that you can have. So there will be no particle production. The number in any scattering process, the number of incoming particles will be the same as the number of outgoing particles. And in fact, the set of incoming momenta is the same as the set of outgoing momenta. You just have a reshuffling of the momenta among the particles that appear in the scattering process. And finally, a very important requirement is the fact that you have factorization. So an n-body scattering event can be decomposed into a sequence of 2 to 2 scattering events. So this tells you that for an integrable theory, the really interesting property is this 2-to-2 scattering matrix, because then you can reconstruct the end-to-end scattering amplitude just by looking by taking the product of these 2x2 scattering matrices. An important consequence of this factorization is that this two-body S matrix needs to satisfy the Yang-Baxter equation. So this you can see by just looking at the scattering of 3 particles. So this is this picture in the middle, and because you can decompose it into scattering, 2-to-2 scattering in 2 different ways, so the pictures on the left and the picture on the right, well, consistency tells you that these 2 ways of decomposing should give you the same result, and this gives you an equation for the 2-body S matrix. So this left-hand side should be equal to this right-hand side, and this is called the quantum Yang-Baxter equation, and it's really the equation that describes for you an integrable 2-dimensional QFT. Some comments that will be important for the rest of the talk is that in general, when you compute the S matrix for a given theory, maybe you have some parameter in the theory, some coupling, and you expand, you compute this S matrix perturbatively. So you write it as being the identity just for the free theory, and then you have the interaction piece. And furthermore, this interaction piece you can decompose into 3-level contribution, 1-loop contribution, and so on. You can go to higher loops order. This quantum Yang-Baxter equation is an equation for the exact S matrix, or the all-loop S matrix. And if you start computing 3-level, 1-loop, and so on, in order to check integrability, you need to expand this equation, and this gives you, for instance, for the 3-level scattering, you need to check the so-called classical Yang-Baxter equation, which is a consequence of the quantum Yang-Baxter equation, just expanded for each loop order. Another remark that is important for the rest of the talk is that if this S matrix is a pure phase, so something that is proportional to the identity, proportional to the scattering of the free theory, then this Yang-Baxter equation is trivially satisfied and the model is integrable. Also, another important remark is that this relies heavily on having a 2-dimensional QFT, meaning that if you have, for instance, a 3-dimensional QFT or 4-dimensional QFT, this notion of factorized scattering doesn't appear anymore. So we don't have this notion of integrability for higher dimensional QFTs. All right, so this was like a crash course on integrable theories, and these were the most important notions for the rest of the talk. So let's now look at what has been done for the Nambu-Goto string and discuss its integrability. So the starting point is the Nambu-Goto action that you're very familiar with. So that is written here. It is proportional to the area that is swept out by the 2-dimensional worldsheet of the string. So here T2 is an overall constant, which is the string tension. Then you have an integral over the 2 coordinates sigma 0 and sigma 1 that parameterize the 2-dimensional worldsheet of the string. This gamma alpha beta, so the fields x mu that appear here are the target space coordinates, and this index mu goes from 0 to capital D minus 1, where capital D is the dimension of my target space. So here capital D is left for the moment unspecified. So we look at strings that are not necessarily in critical dimension, but also in other dimensions. So if one wants to compute the scattering for this type of theory, well, we first need to fix the reparametrization invariance on the 2-dimensional worldsheet of the string in order to have a well-defined 2-dimensional quantum field theory. And this you can do in different ways, but here one can fix static gauge, which means you expand around having a long string solution. So you fix 2 of the target space coordinates, you put them to be equal to the 2 direction on the worldsheet. This leaves you then with the transverse coordinates, so you have then capital D minus 2 because 2 of them were used in the static gauge fixing, and these coordinates then represent the the oscillation or excitation in directions transverse to this long string. And this is the scattering that we want to compute. We want to compute how these transverse coordinate interact with each other. So to proceed, this is best done in perturbation theory. So this action, the Nambu-Goto action in static gauge, it can be expanded in powers of the field, or equivalently in inverse power of the string tension. So there will be a constant contribution. There will be a contribution that is quadratic in the fields, a contribution that is quartic in the field, and so on. You will have an infinite number of interaction terms with an increasing number of fields that appear. So here, the quadratic piece is actually the Lagrangian of a free theory, so of a free collection of massless bosons. And the first interaction term is a cubic order, and it takes this form. So there are two types of interaction terms that can arise depending on how the Lorentz and targets, well, the SOD indices are contracted. And to make the link also with the talk of this morning, this Lagrangian, you can also obtain it as starting from the symmetry breaking pattern of what your long string. It breaks the target space Poincare symmetry down to the two-dimensional Lorentz on the worldsheet, and then rotations in direction transverse to the string, and these fields xj are then the Goldstone modes associated with the symmetry breaking pattern. So this is another way of seeing this action. All right. So then, with this free quadratic term and with this cubic interaction term, you can start looking at interactions. And here I will look at the 2-to-2 scattering, where two incoming bosons xi and xj with momenta p1 and p2, and two outgoing bosons xk and xl with momenta p3 and p4. So this scattering amplitude is best written down using the Mandelstam variables. And it takes the following form. So here there are three terms that appear depending on how your SOD indices are contracted. So those are these terms A, B, and C. A has some interpretation in terms of an annihilation of particles. B would be the transmission of the particles. So you see it's proportional to like the identity in this SOD structure. And C would be the reflection coefficients. And of course, you have the conservation of the momenta, so energy and spatial momentum. There are some crossing relations between these coefficients A, B, and C. So once A is computed, B is obtained from A through exchanging the Mandelstam variables S and T, and C is obtained from A through changing the variables S and U. So once you know A, you can deduce what B and C are. So let's look at some results. So for the tree-level amplitude, so these are the values of the coefficients. A is proportional to TU, B is proportional to SU, and C is proportional to ST. So I used the upper script 0 to indicate that this is tree-level. Later we will see the one loop case. In 2 dimensions, so here we are working with so this is the string case. So the worldsheet is 2-dimensional. There is only one independent Mandelstam variable, so you can fix T equal to 0, U equal to minus S, and this simplifies the scattering, and the amplitude becomes just proportional to the identity. So only this coefficient B is turned on, A and C are equal to 0. So you see that there is some structure that starts appearing. Now let's look at the one loop case. So there are two types of diagram that contribute to the one loop scattering. One is the tadpole diagram that comes from the vertex involving 6 fields, but you can show that this actually vanishes, so we don't need to consider it. The other types of diagram are the bubble diagrams, so the S channel, the T channel, and the U channel. And one needs to compute the contribution of these 3 diagrams to the one loop amplitude. And so this is the result also by Sergey in 2012. So those are the values of the coefficients A, B, and C. And there is some interesting, so here the Mandelstam variables are chosen so that it respects the 2D kinematics. So T is fixed to 0 and U is equal to minus S, which is something we can do because this is still for the string. And you notice, so the hat was the number of transverse fields, which was the target space dimension D minus 2. So you see that this scattering amplitude then becomes proportional to the identity in a target space dimension D equal to 26 because the coefficients A and C vanish and you're just left with the coefficient B. So this is some simplification that appears in the critical dimension of the string. Another observation that was made later is that in other dimensions D, so not necessarily in the critical dimension, you can actually get rid of these terms A and C by adding some term, some counter term to the Lagrangian that is of higher derivative, but with the same number of transverse fields. However, this term actually breaks the nonlinearly realized target space Lorentz symmetry. So this is.
Is this related to the knowledgeable light quantization?
Yes. So yeah, exactly. So I will come to this in the next slide. So these 2 statements are actually true at all loop orders. So this is a one loop statement, but you can go to higher loops and check that this is true at all loop orders. And let me now summarize this. So you have these 2 lines, two lines of theories. One is this orange line that is the one that you obtain just by computing the scattering from the Nambu-Goto action in static gauge. And there is something special that happens in D equal to 26. And the other line is the line of integrable theories, so the one where you add this target space Lorentz breaking term, but which has a pure phase S matrix for any dimension D. Also a remark is that here I always assume that capital D is greater than 3 because something special happens there, because you basically only have one transverse field and the theory is integrable. And as Gabriele was pointing out, the fact that you have this line and you can add this term in order to make the theory proportional to the identity is related to the fact that these theories arise from this TTbar deformation of a free theory. So let me explain this in more detail. So the TTbar deformation is a one-parameter deformation constructed out of the energy momentum tensor. So when you have a quantum field theory which is local, so which has an energy momentum tensor, you can construct this operator O TTbar, which is the determinant of the energy momentum tensor, and you can then construct, at least classically, this Lagrangian that satisfies this differential equation. So this Lagrangian would now depend on this parameter lambda, which is the deformation parameter that you introduce, and this is the differential equation that it satisfies. So how can you think of this type of deformation? Well, it's easiest to look at it from an infinitesimal point of view. So you start with a Lagrangian at some specific point, which we identify as your undeformed theory, so with this deformation parameter lambda being 0. And then you start solving this differential equation for a small deviation delta lambda. And this gives you a new Lagrangian, which now depends on delta lambda. And from this new Lagrangian, you can start computing the energy momentum tensor for this whole right-hand side, not only the lambda equal to 0 piece, but this whole right-hand side, you construct the energy momentum tensor, you construct this operator or TTbar, and then you iterate the procedure like this, and you obtain finally a Lagrangian that is depends on lambda in a finite manner, not only here with this infinitesimal deformation. Some properties of this type of deformation. So, as I already mentioned, it can be applied to any two-dimensional theory with an energy momentum tensor. Another feature is that when you apply it to a CFT, a conformal field theory, then the theory of the deformation may no longer be a CFT. In terms of RG flow, this corresponds to an irrelevant deformation. So if you start from a theory in the IR and you start deforming with this TTbar deformation, you will flow towards the UV. And in 2 dimensions, this operator or TTbar is well defined at the quantum mechanical level. So this is a non-trivial statement because you see that when you take this operator, you need to take 2 operators, 2 copies of the energy momentum tensor at coincidental points. And this is not necessarily well defined because you might have divergences that appear, but it has been shown that this is an operator that is well defined at the quantum mechanical level, at least so this is for dimension d equal to 2. It's not known yet how to define TTbar deformations at the quantum level for theories in higher dimensions. And this line, let's see. Oh, okay, so yes. Another property is that the S matrix of these theories of the deformation, it's given by the theory before deformation S naught, dressed by some CDD factor, something that is a pure phase. And the consequence of this is that if you start with an integrable theory, so if S naught is integrable, if it satisfies this quantum Yang-Baxter equation, you deform it with this TTbar operator, you obtain a new theory that is interacting, but again, it is integrable because it will also solve the quantum Yang-Baxter equation.
But this is not specific of integrable theory.
This one?
Yes.
So this is specific to TTbar deformations.
But not of integrable.
No. There are integrable deformations where you start from S naught that still depend on one parameter, but the new S matrix will be something that is completely different from just having a phase times the undeformed S matrix. So this is specific to TTbar deformation.
So Fiona, you mentioned a certain point that this TTbar deformation is related to that other way of cancelling the A and C terms, and you mentioned that to cancel those terms, the string action will no longer be a linearization of the Poincare group.
Yes.
So this breaks the Poincare group.
Yes, it does, yeah.
So, but then in the case of the effective theory of Yang-Mills, would you have something like that? I would not expect that you can have something like that. The original theory is Poincare invariant.
No, it only works in d equal to 26, where these 2 descriptions coincide, or also in d equal to 3, which is special because it also...
Oh, I thought you could cancel those terms with this term also in d different.
Yeah. You can cancel those terms in arbitrary d.
Say d equal 4.
You can do it with d equal 4, but then you don't look at QCD anymore.
Okay.
Because it's something different. You don't have the same symmetries.
Yeah.
And to make the link more manifest with what I was saying previously, is that you can start looking at what the TTbar deformation of the L2 is. So this free collection of bosons. So if you assume that your initial theory is this collection of free massless bosons, then you can look at the TTbar deformation and you can actually write down an action at the finite for a finite deformation parameter lambda, and it takes this form. So you see that there is a direct relation with Nambu-Goto in static gauge, which is just this first piece here. And this explains why there is also this simple phase factor in this case. So yeah, I want to stress this you can do for arbitrary dimension D here. When I start from this Lagrangian and deform it in that way, the target space dimension or the number of transverse field is not specified here. So this is true for arbitrary dimensions D. All right, so this is the second line in this diagram. So those are the TTbar deformation, and this is the Nambu-Goto string. So this was the story about the Nambu-Goto string and the relation to this integrable TTbar deformation. And then one question that you can start asking is what happens when you consider higher dimensional objects? So for instance, P-branes or the membrane. So what can be said in dimensions that is higher than 2? Because as I mentioned, TTbar deformations are only kind of well understood in D equal to 2, and also this factorized scattering, this Yang-Baxter equation is only understood in D equal to 2. So what actually happens in dimensions higher than 2? So classically, you can still define a Nambu-Goto-like action, where now instead of having worldsheet coordinates, you have worldvolume coordinates. So I introduced this little d, which describes the dimension of your base manifold, if you want. And again, here, same as for the string, you can fix static gauge in a similar manner. So this would mean you expand, for instance, if you have a membrane, you expand around a vacuum with a flat membrane, say. And again, you're left with a set of transverse field, where now the number of transverse field is given by the target space dimension minus the dimension of the base manifold or the world volume. So let's specialize to D equal to 3, which describes a membrane, which might be interesting because it's kind of a fundamental object in M theory as opposed to string theory. And in that case, so again, the strategy is the same as before. You take this action, you expand in powers of the fields, and the tree-level scattering is actually the same as for the string case. So we again see these coefficients A, B, and C appearing. But here, because you have, this is a 3D scattering process, you cannot impose these 2D kinematics of having t equal to 0, and u is equal to minus s. So all of these coefficients contribute. You don't have something that is just proportional to the identity. So this is the first difference with respect to the string. So then at one loop, what happens at one loop? Well, let's just look at one of these coefficients, A1. So here I've wrote the result explicitly, so just that you get a flavor of how it looks like. And so the conclusion is that there is no real special value of d hat or d for which this amplitude becomes particularly nice. So contrary to the string, where something really interesting happened for d equal to 26, this doesn't seem to be the case here for this higher dimensional object. In particular, even when you start restricting to 2D kinematics because you can do it, by fixing these Mandelstam variables, you still don't have a process that is diagonal. So you still have A that contributes, A and C contribute. All right, so this is for just looking at like bosonic membranes. And in a work in progress, so these are quite some recent results, that we got is what happens if you include fermions and look at the supermembrane instead. And then you actually see that, from a computational point of view, you can do all of what I said before. Also in this case, one subtlety is that the static gauge on the bosons, you need to complement it with a kappa gauge on the fermions, so that you have the correct number of physical degrees of freedom. But this is just a technicality. And you can compute the one loop amplitude. So again, you take your external particles to be the massless bosons, but now in the loop, you have both the bosons that contribute and also the fermions. And then actually something very special happens for d equal to 11, which is the critical dimension for the supermembrane theory, and the amplitude becomes proportional. So the one loop amplitude becomes proportional to the tree level 1 with some proportionality factor that depends on the Mandelstam variable. And in fact, restricting to 2D kinematics in this case gives a diagonal scattering. So for the tree level, we have seen the scattering was the same as for the string. So of course, when you start looking at just 2D kinematics, only the B coefficient will contribute and you have a diagonal scattering. And here, well, because it is proportional to this tree level case, also this will still hold at one loop. So this is an interesting observation. We still need to understand what all this means. But I think it's nice that there are some simplification that seem to happen in d equal to 11.
You have an expression for general D, just to appreciate how much simpler it gets.
Yes, I do, but not on my slides, but I'm happy to show it afterwards.
There's no other T where simplification appears?
Other D...
D equals 3, but the D equals 3 it's...
well, d equal to, I mean, it could be d equal to 4.
D equal to 4, right?
I looked at it, but it doesn't, well, yeah, I'm not sure. I can look at it. I have some expressions, but yeah, basically what happens is that here there are some cancellations. So there will be the number of spinors that appear, which is proper. I mean, it could be like 16 if you have or Majorana fermions, and then it starts cancelling some of these terms, and you have just d hat minus 8 that appears, and therefore this is which is special for, which means that d equal to 11 is special.
But when you say that you can see the supersymmetric membrane, because one can play with different number of supersymmetries.
Yeah.
So
this is supersymmetric. So this Vasumino term that I add to the action, it's with this special coefficient, so that I have supersymmetry and kappa symmetry and so on. Yes.
But did you try to see what happens? So that's presumably that's the supersymmetry, which
supersymmetry.
matches the one which you have in M theory, right?
Yes.
But in principle, one can consider some general supersymmetric cosine, right?
Yes.
So is it special?
I have the expression for general coefficient in front of the Vasumino term, but I have not analyzed it yet. But so there might be something special happening here. But yeah, this is for the supersymmetric case.
The expectation in W is finite. One loop, I guess, is like for the string.
Yes.
So higher loops, it's always finite in theory or not?
So to one loop, it is finite on kinematic ground. At two loop, there might be divergences that appear, but some calculations have been done, and it seems like it is finite. So one could also look at that here and go to higher loops. But at higher, if you want to compute higher loop orders, you need to start to include also interactions of 4 fermions, and it becomes quite complicated. But the expectation is that it should be finite.
Where does expectation come
from? Well, okay, so it's probably, maybe not for the flat membrane, but for like M theory in curved spaces, it comes from ADS4 CFT3 duality, because you can compute quantities on the for ABJM theory using localization, and this results.
No, this is just a statement that membrane can be quantized. It doesn't, just like for string, right? For critical string, we also know it can be quantized, but if one start doing calculation with Nambu-Goto, like at 2 loops, you find divergences. It just that expectation just tells you that there is a consistent prescription how to fix counter terms and derive a meaningful theory. But it doesn't, I don't think it tells us that we expect just doing straightforward loop calculations to get finite results. So.
Yes, yeah, okay. So it just suggests that there is a way of obtaining a finite result.
But maybe what you have in mind is that you take some flat space limit of some observable areas for CFT3 duality, and that supposedly should produce the finite answers that you will get this way.
Yeah, I suppose I don't know technically how to take this flat space limit.
But what you have in mind is the flat space limit. connection to the ASC?
Yes.
Okay. Have people done like a counter-term type analysis for what kind of divergence can show up for the super
I
membrane?
don't know. All right. Yeah, and a question is whether this type of structure where the amplitude simplifies, if it persists at higher loop order, so when you start going to 2 loops and so on, and whether you can, on these grounds, postulate some exact S matrix that would describe the scattering of excitation, similarly to what could be done for the string case. But those are open questions. I cannot answer them now.
But that would be exact as matrix in 2+1 dimensional theory.
Yes.
That would be pretty ambitious.
Yeah. But yeah, I mean, it's just some open question. All right. Now let me come to the part of the talk where, so all this was for the 3-dimensional, so this part was for the 3-dimensional.
So it's a right question.
Yeah.
So at the same order, presumably also get some 2 to 4 scattering. Right? So here you talk about 2 to 2 S matrix.
Yes.
But there are some 2 to 4.
There are some 2 to 4. Right.
Just from 3 level, right? The same order.
Yes, because of the L6. So yes, there will be terms where you don't preserve the number of particles, which might prevent you from constructing an exact S matrix. I mean, because the exact S matrix would be something that preserves the number of particles. But yeah, I mean.
No, I'm just trying to understand, like, really, what is the special thing which happens at D equal 11?
Okay, so the only statement is that if you look at 2 to 2 scattering with external massless bosons and fermions in the loop, then the 1 loop scattering becomes proportional to the 3-level scattering. That's the only statement. Then what this means, as I said, is we don't know yet.
Does it satisfy unitarity?
Yeah, yes,
Because
it will satisfy unitarity.
And then also the 2 to 4 somehow have to cancel, right?
If it satisfies unitarity, then also the 2 to 4 should cancel. So I'm actually in the process now of looking at what unitarity implies for if there is just a coefficient, just a function here for what this actually implies. Yes.
So Fiona, yeah, the fact that the 1 loop is just the product of A0 times a nice function. Yeah, what does it imply physically in terms of the angular dependence? I mean, still T depends on angle. And so,
yeah,
I don't see what. Yeah, I'm trying to understand what this mathematical result implies physically.
Yes.
Even a disorder.
But it's intriguing that it happened. It's intriguing that it happened.
It's intriguing. No, I'm trying to. Yeah.
I don't have yet an explanation of this. This is kind of a recent result, and we're still trying to understand.
Sorry, I'm asking a question from an outsider. And what about the relation? Why? I mean, in 1+1, you know that the Coleman-Mandula theorem applies a different way. In 2+1,
yes.
Instead,
yes.
Anyone who plays billiards knows that you have an arbitrary angle of scattering when you. I mean, that's an identity of.
Clearly, it's not integrable theory. I think there is 2 to 4.
Yeah, this is not. Yeah, this is not.
Right, but it's intriguing that something special happened. So,
yeah.
If you're just talking about this kind of linear relation between 1 loop and 3, I thought this is kind of generic phenomenon when you talk about super amplitudes. Like there's a structure that allows you to kind of factorize the 3-level piece from the general higher loop amplitude. This you can see explicitly when you work with this spinor helicity variables. There's a super version.
But this is also what happens with soft theorems.
Yeah.
Okay, because but there it factorized because these are processes that happen on different times. There's a separation of scales between the hard scattering and radiation.
Yeah, but in this case, I would suspect this consequence super solution.
Okay.
But still, it's only D equal to 11 or something. All the supersymmetries are all present in any number of dimensions.
That's true.
So there is something behind it. It's something
Has to be.
some additional.
But let's say that to understand what it means, can you try to guess what would happen when it would become? I mean, what should happen at higher order? So you would expect that, for instance, if 2 loops, 3 loops, they're all like that. So what do? You assign, you get, I don't know.
Yeah, those are all.
Can you fancy where you would be going with a result like this? That's the question.
Maybe there's a hint we use compactify 2D. Is that what we're gonna?
Okay, so this is actually the only slide that will be about the supermembrane, because I thought it's an interesting result and I wanted to show it to you. But as I said, we don't yet understand it properly, but I just wanted to show it to you. And the compactified story now will be just bosonic, and we're working on the supermembrane case and see what happens there.
Because a priori there is no argument why something special should happen, because the difference with a string, in string one can take decoupling limit, like can take just to zero limit, and you get unitary theory on the string. In M theory, you don't have such a parameter. There is no theory which just lives on the membrane. But so it's interesting.
When you talk about the Western middle term, what do you mean precisely? The coupling to the theory, or?
So when writing the supermembrane action, there is the term that is very similar to the Nambu-Goto. Okay, no, C3 is always set to 0, but there is this so the supermembrane action has like 3 pieces. One is the one that is very similar to the Nambu-Goto case, and then there is another one involving the fermions, and then there is this C3 piece. So I put the C3 to 0, but the Vesumino term is the second piece.
So we mean the supersymmetric version of the C3, which does not vanish with C3.
But
I thought the Western, so maybe I'm confused with terminology. Usually by Western middle term, people mean the C3.
Okay, I thought there were 2 terms that you could add, but maybe it is the C3 term.
Yeah, I think it's supersymmetrized version.
So it's this term that you need to add in order to have kappa symmetry.
Yes.
Yeah, okay. So this is the one that I mean.
Okay.
Yes. But I thought that you could also have a coupling to some external or some
C3, yeah. C3.
All right. So let's go back to bosonic membrane and look at the compactified theory. So because these scattering amplitudes were for a 3-dimensional quantum field theory. So we don't have the tools from integrability to say anything about them. So the idea here is to get an equivalent 2-dimensional description and look at integrability in this compactified theory. So I will assume that the target space has one compact dimension, and I will assume that this target space is one of the directions that is used for the static gauge fixing, so that also the worldvolume becomes has the topology of R2 times S1, and then you get by dimensional reduction, you get a theory in 2 dimensions where the massless modes couple to an infinite tower of massive Kaldis-Klein modes. And we want to understand the scattering of these massive excitations. So some technicalities. So the fields are expanded in Fourier modes, and then integrating out over the 3rd direction, which is the compact one. This gives an effective 2-dimensional field theory, where now the quadratic and cubic terms involve the masses of the fields. So for the quadratic piece, this is now a theory of free massless plus massive bosons, and then L4 also is modified and involves these masses. So what about the scattering of this type, where now the external particles can also be massive? So in this case, let me just show you the amplitude A0, which takes this form. And here, so because again we are in 2 dimensions, there is only one free Mandelstam variable. So there is of course the STU is the sum of the mass squared, but there is then one additional constraint that you can impose. And the conclusion of this is that the amplitude is not proportional to the identity, and you can also check that the Yang-Baxter equation is not satisfied. So this is so this compactified membrane theory is already non-integrable at 3 levels. So this is a kind of a classical statement. So let me see how I'm doing this time. Still have. Well, okay. Yeah, maybe I have time to say something about this. So this was at 3 level. You can still do calculations at 1 loop. So this would be the calculation where you have 4 massless bosons as external legs, but in the loop there are the massless bosons, but also all the tower of massive fields that contribute. So these are these coefficients. A, B, and C in this case. So there are some complicated function of the Mandelstam variable S that appear. You can look at some limit. So you restore the radius of compactification. You use theta function regularization to sum over all the masses n in the loop. One interesting limit is to take the limit where the radius of compactification goes to infinity. So this is the result for this coefficient A that you get, and this is the same as the restriction to this 2D kinematics of the 3D amplitude that I was showing before. So the one where I was saying there is no nice D for which things simplify. Another limit that is interesting is the limit where the radius of compactification goes to 0. So this is then the result for this amplitude A1. And this term here is precisely the result for the Nambu-Goto string. So there is also a divergent piece, but this actually cancels once you include also the Stadtpol diagram, which is now a non-zero because you can have propagation of massive boson in the loop. So this result is the same as for the Nambu-Goto string. Another thing is that, so this theory is not integrable, but you can compare it with some other integrable theory which has the same free spectrum, which is the one that you get from just doing the TTbar deformation of the quadratic piece L2. So you start with a theory that is describing the massless and the tower of massive fields. You start TTbar deforming it. So for the Nambu-Goto strings, there was an expression for finite deformation parameter lambda. This is very difficult to do in this case because of these massive fields, but still, for these purposes, for our purposes, it would be enough to look at just the infinitesimal deformation and computing the stress energy tensor, computing this TTbar deformation, you get a new interaction piece L4 that I would call L4 prime. So this would be the interaction term that gives rise to an integrable theory. This is TTbar deformation. And it looks like this. So this is a bit different from the interaction piece L4 that you had just for the compactified membrane, which was not integrable. But this is a term that gives rise to an integrable theory. Some differences is that here, 2 fields that have contracted indices, Lorentz indices, always have opposite mode number, which was not the case for the non-integrable vertex. Also, here there is only a sum over 2 possible mode numbers, not 3, as was the case previously. So there must be, if you want to obtain this theory from compactifying down a theory defined in 3 dimensions, there must be two delta functions on the mode numbers. So it must be a non-local theory in 3D if you wish to start from a 3D action, compactify, and obtain this integrable vertex. So this is a summary picture. So the 3D membrane action, at the bosonic level, there doesn't seem to be any special dimension D. For the supermembrane, D equal to 11 seems to be singled out, but as I said, we don't understand it yet what this means. When compactifying down to a two-dimensional theory, this gives a non-integrable theory. So the Yang-Baxter equation is not satisfied. This L4, this interaction vertex, is not one that gives rise to an integrable theory. But you can start with the same L2, so this infinite hour of massive fields, calculate a new interaction vertex L4 prime, which is obtained through TTbar deformation. Thinking of this integrable 2D theory as coming from a 3D theory, it seems like this 3D theory should be something that is non-local, as opposed to the membrane action, which is something that is local.
I have a question. The Kaluza-Klein states of your compactified theory, I would expect them to be unstable. So they're not asymptotic states. So in a sense, if you, at the tree level, the mass of the state with momentum N1, say N1 and N2, take momentum 1 and 2, the mass corresponding to N1 plus N2 is N1 plus N2 absolute value. And so the phase space for the decay of the object with mass N1 plus N2 into the excitation with mass N1 plus N2 is 0. So this, at tree level, these guys are stable. They are essentially like BPS. Okay? But I expect quantum mechanically to get a convex behavior. I mean, subadditive, right? Or actually, no. Yeah, I think this is, I think that they should all become unstable, this KK mode. You see what I'm saying? KK mode can decay compatible with the conservation of the momentum, the compactified dimension to the lower resonances. Then you cannot compute the mass matrix for that.
Yeah, here
you're doing a tree-level computation, but when you go to the next order, so for instance, if you compute at tree level only the scattering of the zero frequency, the 0 mass 1, you already don't have integrability.
No, it is integrable when restricting to just the
zero.
The zero
exactly. And if you go at one loop, if you only consider the scattering of the massless ones, is it integrable including also loops?
Loop is the same as the string theory, right? It's the same as the string theory.
But now there are the masses in the
But if you integrate them out, I mean, the statistic theory is the same as the string theory.
The statistic theory at energy below the radius. If you go to higher energies, is the effective string theory with a specific set of higher derivative interactions.
So we have two-level insertion.
So I'm asking what happens in that case. But I would expect that this KK mode, just my bet, is that they're all non-asymptotic states. They decay. If you try to do your scattering, they decay. Say N3 decays, N1 plus N2. So an object with momentum N3 can decay in objects that have momentum that sums up to N3.
I see.
So it can decay, but will it happen for the particular TTbar deformation?
Sorry?
Will it happen for the particular TTbar deformation?
No, but she's asking integrability for, there you're asking integrability also for the scattering of the massive ones.
For this one,
which I claim that may not be needed if these guys are not asymptotic states. If there are no corresponding asymptotic states, there's no S matrix to talk about. So this is my question, okay?
Okay. Here.
The existence of an S matrix requires, first of all, asymptotic states.
Yeah, here we kind of assume that those would be asymptotic states. Though, I mean, but these calculations should still, this one loop calculation should still be fine.
The one loop computation I think is correct because it comes, if you're inclusive, I think, but the one loop computation is correct for external massless lengths.
Yes, but this is the result.
And this is not integrable.
No, it's not.
Okay, very good. Fine. That makes it clear.
Yeah, I might be wrong, but my recollection that one can even start asking simpler question. Let's take Nambu-Goto and let's, on the worldsheet, let's add like arbitrary one massive mode. Is it possible to do it preserving integrability? And I think we checked it, and the answer seemed to be no. The moment you add one massive field, then there is no way to keep it in.
But one you cannot, okay?
Right.
So, but this, sorry, perhaps I should not ask because I'm outside of the example that Victor was talking about in November. So your action.
No, but that's another way around. The action, when it's massless, it gives integrable theory.
Okay, when it's massless.
Right.
But it doesn't matter. Okay. It's the massiveness.
Very good. Yeah, so this is the summary picture, and I'm going to an end. So let's look at the conclusions and the outlook. So one conclusion is just that the relation between the effective field theory of confining strings, the Nambu-Goto action in static gauge and integrable TTbar deformations, this interaction between these three different perspectives, it was very useful in order to obtain new predictions about this flux tube spectrum. And here, this talk was looking at generalization to higher dimensional objects. So when you have a membrane instead of a string, and as I highlighted, there doesn't seem to be any special target space dimensions for the bosonic membrane where things simplify. You can also look at integrability by compactifying one direction on a circle. However, the theory becomes non-integrable already at tree level. You can construct an integrable theory with the same free spectrum through these TTbar deformations. And so some outlook. So what about superstrings and supermembranes? So for superstrings, there has been some results already by Sergey, and now we're looking at the supermembrane. So there was one slide on the supermembrane case for the uncompactified theory, well, when you start compactifying in some limit, you should get back the results for the superstring. All this was for the string or membrane in flat space, but you can also try to compute scattering amplitudes for string and membranes in curved spaces, in particular those spaces that are relevant for ADS-CFT correspondence. For instance, for the membrane, for M theory, it's very interesting to look at the duality between ADS4 and CFT3. Another question is that, as I was mentioning, for this integrable theory that you can construct, this TTbar deformation, if you want to lift it to 3 dimensions, the theory seems to be non-local, but what exactly is the theory? I mean, we didn't write down an explicit action, but that would be also interesting to see what it is. Another direction to explore is to look at ADS-CFT setups where you have confining strings. Because if you just look at, for instance, n equal 4, this is not confining, but you can also compute, look at other settings where you also have confinement. So that's it, and thank you very much for the attention and for the questions.